Welcome everyone to the Next Gen 4 International Forum webinar presentation. Today's presentation on graphite molten salt interactions will be presented by Dr. Nydia Gallego. Before doing the introduction today, Dr. Patricia Pavier. Dr. Pavier is the group leader of the Radiological Materials Group at Pacific Northwest National Laboratory. She's also the National Technical Director of the Molten-Salt Reactor Program for the U.S. Department of Energy. She's also the chair of the Gen 4 International Forum Education and Training Working Group, responsible for bringing you these wonderful gift webinars. So without any further delay, I give you Patricia.
Thank you very much, Bertha. Good morning, good evening, everyone. It's a pleasure to have with us Dr. Nydia Gallego. She's a distinguished research scientist in the Physical Science Directorate at Oak Ridge National Laboratory in the United States. She earned her master and PhD in material science and engineering from Clemson University, and she joined Oak Ridge National Laboratory in December 2000. Her research interests include, among others, physical and chemical properties of carbon materials, effects of neutrons irradiation on graphite and carbon materials for use on space power systems. Currently, Nydia is the Oak Ridge National Lab technical lead for the graphite activities for both the gas-cooled reactor and molten-salt reactor campaigns funded by the U.S. Department of Energy Advanced Reactor Technologies program, and she's also the task lead for production of carbon-bonded carbon fiber components as part of the radioisotope power systems program, which is funded by NASA. So without any delay, Nydia, I give you the floor. Thank you very, very much for presenting this webinar. Thank you, Nydia.
Thank you. Thank you, Patricia. Thank you, Berta. Can everybody hear me okay, I hope?
Yes, we can.
Thank you, Patricia. It is a pleasure for me to be here this morning, this afternoon, presenting this seminar. I wanted to, first of all, remind everybody that this was intended to be the second on a series of two webinars related to graphite materials. Last month, Dr. Will Wines from Idaho presented a webinar titled Overview Nuclear Graphite R&D in Support of Advanced Reactors. And in that discussion, he covered in great detail graphite irradiation behavior, oxidation, and some more background on the various reactor concepts that utilizes graphite. He also talked a little bit about the myths about whether graphite burns or not, and mentioned that the second webinar this month will be talking on the graphite molten-salt interactions. Before I go into, and I should point out that a recording of that presentation, as Berta mentioned, is also available in the GIF website alongside his slides. Before I go into the technical details of my presentation, I would like to acknowledge the ORNL contributors to the work that are going to be presented. Primarily, I would like to acknowledge contributions from Christian Contescu, Jisoo Moon, Yusuan Shan, Jin Kaiser, Adam Willoughby, Dino, Junkyu, Shinhin, who had contributed significantly to the work that, again, I'll be presenting here. We also collaborate not just with this core team, but other ORNL members, and within the campaign and outside. And we have collaborators at Idaho, other academia and industry organizations. Financial funding from the work that I will be presenting, it comes from the U.S. Department of Energy, Nuclear Energy, Advanced Reactor Technology Program, and some other work that I will be presented also use resources at the High Isotope Reactor, which is a U.S. DOE Office of Science User Facility. Again, very grateful to this wonderful team of collaborators that I have. Before I go into details about a couple slides from Will's seminar last month, just to put everybody into context, will give a nice overview of what is called now the nuclear renaissance, and mention the various reactor design concepts that are part of Gen 4. And there is quite a few of them that utilizes graphite at the core, not only as a moderator, but also some structural roles in there. He also went to details that some of these high temperature reactors that use graphite at the core can either be cooled by gas, in the case of the helium gas-cooled reactors, or could be utilizing a molten salt as a coolant or also as a carrier for the fuel. With that, I will a quick overview or outline of what I will be talking today. I will go back and do a quick review of the nuclear graphite materials and the microstructure, emphasizing the microstructural features that are of interest to the topic of this, which is the salt graphite interactions with molten salts. And then I will be covering in detail two main topics that are critical for the ASME code qualification of graphite for use in high temperature reactors, which is understanding the graphite salt intrusion, the salt intrusion into graphite and the effect that this may have in graphite properties, and understanding graphite wear behavior. This goes along with graphite and erosion. So we've been tackling wear behavior and hoping to get into erosion topics following this. And I will have a slide summarizing on ongoing activities. With that, just a quick, most people, I'm assuming here, that are present, probably familiar with the graphite microstructure. Graphite crystal structure is a hexagonal compact AB layering. However, the actual manufactured graphite or blocks of graphite is a more complex structure. We got filler particles or cooked particles in most cases. We had a binder material that puts together this, and then this is molded using various techniques. Can be extruded, vibromolded, isopressed, and during that process and a cycle of heat treatments. During that process, there is a significant amount of pores that are entrapped or developed due to the outgassing of the binder. Most graphite, manufactured graphite or nuclear grade graphites will have about 20% porosity. So this is 1/5 of a block of graphite is actual pore structure. Why do I emphasize this, and why is this porosity in graphite important? This is important because this porosity defines the radiation behavior of graphite. The very typical and unique behavior that graphite has with irradiation, where graphite has a negative dimensional change. There is a shrinkage on graphite as the neutron dose increases until there is a point where that what we call accommodation porosity and the amount of defects that are being generated due to the radiation reaches a minimum. And then there is a turnaround point where graphite will start to expand again, and then it comes and cross over to the original dimensions, and then in theory it will continue to expand and will go above the original dimensional. This is important because this typical behavior is going to be a function of the graphite grade, and I'll explain later what I mean by graphite grade. But that graphite grade is linked to a porosity, a typical porosity to that grade that is going to be defined by pore size and distribution. That turnaround point here in this dimensional versus neutron, those will determine the lifetime of the graphite in the reactor. This is, again, is going to be a function of grade, and it's also going to be a function of temperature. This porosity in graphite also is going to lead to external surfaces or edges. In graphite, we're going to have basal planes, and we're going to have edge sites. The edge sites are going to be the reactive sites on graphite. And as you can imagine, when you have pores of different sizes, we're going to have different amount of edge sizes, the surface area. and therefore their oxidation rates are also going to correlate significantly with what the type of porosity or the size of the porosity in that graphite grade. We will have different oxidation rates depending on your graphite grade. Again, and this is very important when we're talking about gas-cooled reactors, because as you may know, helium is not 100% inert. There may be trace amounts of impurities in the helium, and then that needs to be accounted for to understand the oxidation rates. And also in the case of oxidation scenarios, it's important to understand how that graphite will be oxidizing. But when it refers to molten salt, those pores might mean that salt may intrude into the pores, and as salt intrude into the pores, that may also be affecting the graphite properties, whether it be mechanical or thermal. There may be also, again, edge sites that may be susceptible to the interaction with the various components of the molten salt, and this edge site may also be potential sites for either treating retention or reaction with other off gases in there. I think I mentioned several times that when we talk about nuclear graphite, we talk about grades. And then we have there's a significant amount of graphite grades available there, even though they all may meet the requirements for purity and be all close to 100% pure carbon, but they are a quite significant wide range of graphite grades. The main difference for the purpose of this seminar that differentiate these grades, or what I want to emphasize, is that these grades will have porosity that comes in different shapes and sizes and connectivity. The table below will list, it's not a comprehensive, but it's a summary of some of the more relevant graphite grades that are currently being produced. H451 is a historical grade, but we have the MBG18 or 17, PC8, IG110s from the various manufacturers, either from US, Germany, France, or Japan. And the classification on class here is from the ASTM standard, that basically defines the grain size of the graphite based on the size of the failure particles that were utilized at the beginning. This grain size, together with this forming process, again, can be extruded, vibromolded, or isomolded, is going to define that network or pore. One way to characterize that pore network is to do mercury intrusion. And again, this mercury is ideal for characterizing pores that are on the micron size. Here, this graph on the right shows the mercury intrusion data for 12 graphite grades. And as you can see, the profiles of that cumulative volume of intruded mercury versus mercury pressure, we have different patterns in here. We can separate this into two groups. We have the fine-grained graphites that shows a very sharp uptake once this threshold pressure is achieved. You don't see any mercury intruded into the pore structure at these lower pressures, but once you achieve this a given pressure that is typical or specific for each graphite grade, we see this significant uptake. Again, this is a sign or indication that again, first of all, we have very small pores, so graphite is mercury is not waiting in graphite, so we have to overcome that force to not wanting to go into the pores. But once we reach the pressure that let us into mercury into the pores, we'll see that the pores are highly interconnected, and then basically what we do is saturate the graphite because most of the pores are connected. Contrary to this, we see the medium and large grain graphites, where we see a wider distribution of the pore sizes. These graphite grades will have pore sizes that are tens of microns in size, and we see that there's mercury intrusion for very low pressures, and we see that continuing to over this wider pressure range. and this is the whole complete graph for those 12 graphite grades. With this data, we can apply Washburn equation and the model that the Washburn equation used, and pore sizes and pore geometry, and derive the pore size distribution based on mercury intrusion, and that is in this graph here. As we can see, we can observe here two patterns. The fine-grained graphite shows a very narrow pore size distribution, very sharp and narrow distribution, basically telling us that most of the porosity is within this narrow pore size. And the sizes, the average pore diameter for this graphite grades, like I mentioned before, it's on the few microns. Complementing that, the medium and large grain graphites will have a broader pore size distribution, and again, we have pores that will be tens of microns, and in some cases, a few larger pores than that. How do we go from mercury intrusion into salt intrusion? There is a ASTM standard within the community. A few years back, there was this development. It is not a standard test method, it's a standard guideline, and it primarily defines the apparatus and the procedure for exposing graphite specimens to molten salts at high pressures at temperature. And the ASTM also introduces two quantification parameters, the D0 and DT. These parameters are just a ratio or fraction of the either open total porosity, a fraction of the open porosity or total porosity that was covered or filled with salt based on the weight changes of the sample before and after the salt intrusion. Unfortunately, the guide does not specify any sample geometry or size, and it does not specify any equilibration conditions. On the most recent revision of this standard guide, a note was added just to bring the attention to the user that the user needs to be cognizant and aware that literature values that may bring up the parameters into it needed to be taken into consideration, that there may be differences in sample size, geometry, or equilibration conditions that may lead to different parameters. The one deficiency that, in my opinion, the guide has is that the guide does not make a reference about where the salt or makes reference to the fact that the salt may be distributed or uptaken by the sample in different conditions, and therefore may be distributed different across the sample geometry. And again, all that because of what I spent a few minutes explaining, the variations on pore size and distribution. At ORNL, we have developed our capabilities to expose graphite samples to molten FlyNac. Our system was developed and approved to operate at temperatures up to 750 degrees C, and we can go up to pressures of 10 bar. Our sample holder and everything that is in contact with the salt, it is made out of graphite just to avoid additional effects or corrosion effects because of metal or alloy components exposed to salt. So everything that touches the salt in this case, it is graphite. But like I mentioned, most of that effort has been focused not on just measuring and quantifying the uptake as a weight percentage or as a D parameter, but on trying to understand once samples are exposed to molten salt, how that salt is distributed within the graphite. For that, we've been doing neutron imaging. We have here at ORNL the neutron imaging beam line at HIFER. So we have taken samples. We did this original proof of principle with samples that were exposed to FlyNac at 5 bar, at 750 degrees C, 5 bar for 12 hours. The samples were a square cross section of 10 by 10 millimeters and 10 millimeters in height. So we have these samples available when our bin time proof of principle time became available. We loaded these samples into the sample holders that are basically just on aluminum cans that are sealed. Everything, once we had exposed the samples to the molten fly everything has been stored in a glove box to avoid, moisture uptake. So those salts, as most of you may know, are highly hydrophilic. So we have everything again is loaded into a glove box, maintained in an inner environment. We take this to our bin line. We have our sample holder here, and then we do our radiography and imaging. The holder will rotate the sample can, allowing for a 360 imaging of the sample. And this image overlaid here basically gives you like a slice, a half of that radiography of those samples. In this case, we have these 4 graphite grades here that will have represent different pore sizes. So we after we done the imaging, we take this and we're able to do a 3D reconstruction. So we had our blocks here. I should probably mention that our neutron imaging basically is measuring the attenuation coefficient. So this color scale here, pure graphite will have an attenuation coefficient close to 0.3. So green alone will be an indication that it's just mostly graphite in there, carbon. The FlyNAC attenuation coefficient of the various components, primarily contributing from the lithium in the salt, will have an attenuation coefficient of close to 0.5. So the more red you see, the more indication of salt being present in that volume. I guess I should have pointed out here that our image resolution was only 75, and therefore, as you can remember from some of those pore sizes, this is much larger than the pore size in those fine-grained graphites. So we'll be getting kind of more of a volume in that box, so volume that we get. But still, I think is, as I'll show, give us very good information on the salt distribution. So we had taken this 3D reconstructed image and gone and do sections or extracted planes from various distances from the top surface, just so that we can understand how that salt is distributed, not only from the outer surfaces, but also from the top bottom. And so we have this graph in here. The first column in here is going to represent the plane closer to the outer surface. And we decided to take this a little, just 0.5, half a millimeter away from the surface because of there's some artifacts on the edges. But again, this represents the plane closer to the top surface, and then we continue to extract planes that are getting away from that until we got to this 7.5, which is the half weight of our sample geometry. And so this particular column will be representing that salt intrusion that is unidirectional from the 4 sides in here. Again, we do have, because of the square cross section, maybe some artifact on the corners of the sample. But I guess to point out here, and again, the scale here is neutron attenuation. The more red means closer to the to more presence of lithium. But a significant difference we see between this PCA, which is a medium large grain extruded. We got large pores in here, and compared to that, these 4 grades in here that are fine grain graphites, where we see that the salt is more concentrated on the edges. And finally, this last one, which is CGV, this is a historical grade that was used in the MSRE experiment. That it was had sealed surfaces, and we can see there is not significant intrusion. So what we've done with this is taking the physical characteristics of the graphite sample before the intrusion and the amount of salt uptaking, and done some normalization. So we had translated this neutron attenuation coefficient maps into what I call here a coverage map. So we took this last plane here, halfway to the height of the sample, and we saw normalization on that, and we translated that attenuation coefficient into coverage from 0 to 1. And as you can see, that the middle plane, again, this follows very similar to attenuation. It's just a different way to look at the numbers. We also calculated the soil coverage percentage, which is basically just a integration of the area under this line profile that it was taken halfway in that plane. And I will point out that you may notice that up to this point, I have not mentioned any weight percentages I've taken. And I've done that on purpose because I didn't want to bias anybody with this have a more or less percentage. We wanted to make sure that we understood more where the soil is going and how that profile is happening, how deep from the outer surface the soil was penetrating. But from this curve under the area under the curve of percentage, we can see that, for example, these two are very similar. We have 20 and 19. There's some errors in here, but our curve under the area, and if I were to correlate that with the percentage of soil uptake, the trends are very similar. But you can see that 20% coverage is distributed very different in the PCA versus the MBG18. ETU10, for example, has a little higher coverage, but that is a little more more concentrated on the edges versus the PCA, which seems to have a little less, but is distributed again over the whole cross section. So additional things that those results that I just presented have been put together into a paper that is currently in the review. So if you're interested in more details or want to go and review this, look into this paper. I hope it will be published pretty soon. One thing that I pointed out when I mentioned the ASTM is that we didn't have guidance on sample geometry or size, and we didn't have guidance on equilibration conditions. And so up to that point, we have been doing intrusion for about 12 hours. We decided to look into is this a fully equilibrated situation, or is that soil uptake is going to change with time. So we went back, applied for additional bin time. We got additional neutron imaging time. At this time, we moved from the square cross sections to eliminate those cornice effects to cylindrical samples. We had samples that were 10 millimeter in diameter by 20 millimeter high. We were able to also do the imaging of the sample prior to the soil intrusion, so we have a true representation of that sample. We didn't have to get averages, we just have that image, so we were able to subtract that from the sample after the intrusion. And we did intrusion in this particular time at 3 bar, 750, and we did the 12 hours, which was our standard up to this point, and then we kept samples for up to 2 weeks at these same conditions. Here, this is just a brief summary of 2 graphite grades, a fine grain graphite, IG-110, and a larger grain graphite, MBG-18. This is how the imaging of the sample prior to soil intrusion looks like. Here, again, we cannot resolve individual pores because of the resolution, and the pore sizes being much smaller than the resolution that we have. But in MBG18, we can see that we can resolve some individual pores, again, due to that broader pore size distribution and the presence of relatively large pores on MBG18. And then we see that at the 12 hours, there is no soil intrusion on IG-110. And after 2 weeks, we don't see any on the IG-110 either. But we see that on the MBG-18, we see some partial soil intrusion in here, but we see a lot more, or significantly more, after the 12 weeks. With this data, again, we now that we have the baseline from the sample prior to the intrusion, we're able to do 3D reconstructions. And this is a reconstruction of the soil after the intrusion. We can see the spots where there may be some soil in the surfaces, and we can go over the volume and subtract the image, the original image prior to intrusion, and just leave behind the areas where that represents the presence of soil. So again, it's demonstrated, how powerful this neutron imaging is for this particular situation, and this great contrast that we have between graphite and the flat night. Okay, but beyond measuring this and imaging, we want to be able to predict soil intrusion based on fundamental properties of the soil and the graphite. Again, I mentioned the wastewater equation before when it comes to that we utilize, that is used for mercury intrusion. The wastewater equation uses fundamental properties of the soil at the temperature conditions, the surface tension, but it also takes into consideration not just the pore size, but the contact angle of that fluid and the graphite surface. Again, surface tension, wetting angle. So our other effort at ORNL within the campaign is to better understand that wetting angle, contact angle. So we had recently commissioned a high temperature contact angle measurement system. Basically, it's a cantilever system. We load our sample in here. We had a furnace we covered here. We pull vacuum several times to make sure we have an inert environment. We flow argon. We bring up this furnace to temperature. And again, we have a camera here. We get a window. We get a light here. And we get a detector where the image projects. And then we can observe the transition from solid to fluid and the changes on contact angle, measure the contact angle and the changes of contact angle over the temperature range that we're doing or over the time frames that we're looking at that. Just to give you an idea, this here is the graphite sample. We're utilizing graphite discs that are about 10 millimeter in diameter, couple millimeter thickness. And this here is the salt. We're pelletizing the salt just to make sure that we have a defined geometry at the beginning to help on the melt process. The salt pellet is about 3 millimeter in diameter, and that is about 8 milligrams of salt in here. Just to point out, the melting point of flanite is about 454. So I got a video here that is just, again, it starts at 400, close to the melting point, and we can see temperature increasing. We're getting close to that melt temperature, and we see after the melt temperature is reached, that salt goes from solid to liquid, and it coalesces into this droplet. The contact angle here is above 90. It's about 130, in the range of 130. That is indication of non-wetting. So up to this point, the salt is not wetting the graphite surface. But as we see this temperature increasing here, and as we approach the 700 and beyond, we see that contact angle, this angle here, is changing with the temperature, and is decreasing. And we see it getting very close to the 90, indication that's starting to wet. We also see the volume of that sphere changing slightly. It's also indicating that some of that salt, again, is going into the pores. And again, contact angle below 90, where there is, the salt went from non-wetting to wetting. So we are doing this. We are looking at various variables, not just the graphite grade. This particular video that I show here is for graphite at G110. We're doing this for the same graphite grades that I mentioned before, the 12 grades, with different pore size distributions to see if there's any effect. We're preparing samples with different surface finish. We're hoping to also do different surface pretreatments, maybe on the surface, to see if there is any change and potentially looking at changing the environment in here to see if that will have an effect, again, mostly on the surface tension of the soil, but how much that will affect the weighting of that. Okay, and one thing also we'll be looking at whether that contact angle will change if it's kept at a given temperature over a long period of time. The second topic that I mentioned that I'll be talking is understanding wear behavior of graphite. And again, some of the reactor composites, we have pebbles that we move that are moving into the molten salt, or will have salt flowing through graphite channels. So wear and erosion are things that are important to understand. We had started to look at erosion, but don't have any data. That's a little more challenging property or issue to address. But we have been looking and doing some proof of principles or initial studies on trying to understand wear of graphite immersed in a molten salt. This is the original setup that we use. It was available at ORNL. It had been used for some solar programs. They've been looking at some chloride salts in there, looking at some corrosion and wear of some alloys in chloride salts. We have access to it to do some proof of principle. We have these graphite pebbles that were provided to us by one of our industrial collaborators. This system is a pin on this kind of geometry. So from these pebbles, we machine these graphite pins. So the surface of the pin will have the curvature, maintain the curvature of this pebble. And then we did the initial studies on a 316L stainless steel. We loaded the salt in a glove box. We seal it. We brought it into this bell jar, brought down the furnace, and flow argon, and then pull out the cap, brought out the pin, and did our wear testing. So we initially compared the same geometry, the pin on and the stainless steel, flowing just argon, and then we added the molten fly nag. This table here just basically summarizes the differences between the wear volume, or whether a test was utilizing argon or we have a molten fly nag present. And the main takeaway here is that when we have what we call a dried environment or inert environment, in this case was flowing argon, the wear volume on the stainless steel was a negative, which basically is an indication of deposition, material deposition from the graphite pin into the stainless steel, which is expected at these conditions. But when we added the molten fly nag, we see that wear volume goes from negative to positive, meaning there is erosion or wear in the stainless steel. And again, there is the presence of salt, there's corrosion. There's not only wear, but there's also corrosion of the stainless steel. So there is a combined tribal corrosion effect in here. Based on this and knowing that we can use the setup that we have, we proceeded to have a more controlled set of experiments. The second set of experiments that we did, we moved from the 316L to a 316H. With conversations with some of our industrial collaborators, they recommended that we look at 316H instead of the L. And we did, this is our matrix. Basically, we did two temperatures, 650 and 550. We did three sliding speeds, rotation speeds. In here, we went from 1, 10, and 100 millimeters per second. We kept the duration of the test constant, and that just to have the corrosion part constant in here, so the time exposed of the exposure time of the 316 stainless steel to the molten salt was constant. And then we added this other condition that we call here floated or starved. And that came out from when we were doing these experiments at the highest sliding speeds. This rotation we noted that at these very fast rotation speeds, the amount of salt that we had initially put in here that was covering the interface was climbing over the sides of the cap, and therefore it wasn't, this interface wasn't fully covered or immersed in the salt. So we went back and did some more control measurements here at the lowest sliding speed, where we reduced the amount of salt to just have a film or similar conditions to where we have here when the rotation was very, very fast. Briefly, I'll go to some of the takeaways of the results. This graph here compares the effect of temperature, and I think a little bit as expected, as we increase the temperature from 550 to 650, we see that the wear volume and the wear rate of both the graphite pin and the 316H flat increases, and again, at higher temperature, the viscosity to the molten salt is lower, and leading to poor lubrication. The corrosion rate of increase from 550 to 650 is more pronounced for the 316H, and this may be, again, more corrosion at higher temperatures. The corrosion rate is higher, but it's also maybe a representation. The 316 soften a little bit or more at these temperatures, and again, more prone to wear too. Looking at the effect of sliding speed, this is a little more complex to understand, and again, as this is mentioning, there's more than one factor here, not just the sliding speed, but the fact that we maintain the time test constant meant that your sliding distance was much longer as you were, your speed was faster, so you have a longer track, or equivalent track over these measurements. I guess the main takeaway here is that these higher speeds, we also observed that at this higher rotation speed, we observed some vibration, and we believe that this higher wear volume on the graphite at these higher speeds may be due to some the effect of vibration, and the fact that, you know, graphite is brittle, so there may be some damage in there due to the vibration at these higher speeds. And then finally, a comparison of the amount of salt in the test. Just to point out, this first graph in here and the last one is basically the same, the original graph that I say, going from argon to the presence of salt, and these conditions of and also sliding speed at the lowest sliding speed of 1 millimeter per second. Again, this we go from having a negative wear volume, which again is a deposition of graphite on the surface of the stainless steel, to having a positive. But we observed that when we have stark condition, meaning we don't have a fully submerged interface into the salt, the wear volume and the wear rates increases here. And again, this is because the smaller presence of salt prevented the formation of a self-lubricating graphite transfer film, and it wasn't able to provide a stable protective lubricant at that interface. All of those results were recently put together, and there is a paper that just got published. So if anybody's interested in looking at those results in more details, please look for this publication. The setup that we have, that we utilized for this, again, was available. It allowed us to do some proof of principle, get some initial data, but we understood that it was the most ideal situation, again, because there's also the possibility that there may be some, the environment is not completely inert. So we have more recently added to our capabilities a new glow box and tribometer. The tribometer is going to be completely enclosed in our glow box, so this will allow us to handle not only the soil but the samples and to do the measurements, and again in a complete inert environment. And so this is just being commissioned. So we're doing some testing without closing the the glow box just to make sure that everything is functional. But we're hoping to have this closed and getting some additional data pretty soon. We will also be interested in looking at other interfaces. So we have done some data on graphite on a steel surface, but we will be interested in looking at graphite on graphite surfaces too. Just coming to the end of my presentation, just a quick summary. I briefly talked on the two main topics of interest here, whether soil intrusion into graphite, how we understand that, how we measure that, how we can get information on how that soil is distributed into the graphite sample. This is critical to guide our efforts in trying to understand how that soil is going to affect the properties of graphite, whether mechanical or thermal properties. We also have some efforts here on trying to understand the more fundamental interactions on the soil and graphite by measuring contact angle and potentially developing predictive models of soil intrusion. We have some proof of principle or initial results on wear testing of graphite in a molten flynac, and we have new facilities that have been installed that would allow us to continue doing this and hopefully expand this to do some erosion testing too. Next slide is just a summary of the various reports and publications that have been derived, published for the past almost 4 years in this program. So the list is here. It's available to you, and you guys get the slides. All of these are available at OSTE if interested. So with that, I would like to thank you and happy to answer any questions that you may have.
Thank you, Nydia, very much. Well, questions are coming in. We'll just take a quick look at the upcoming webinars that we have scheduled. In June, a panel session on the International Knowledge Management and Preservation of the SFR. In July, a presentation on off-gas xenon detection and management in support of MSRs. The July webinar, I'll just give folks a heads up. We're going to test a different platform from our GoToWebinar platform. We're going to test the July webinar on using a Zoom, not zoom.gov, but Zoom. So further registration information will be forthcoming on that. And in August, we'll go back to GoToWebinar, finish out our subscription that we have with this platform, conclude our webinar series for this year with corrosion and cracking of the SCWR materials. With that, we'll open it up for questions. There are several questions that came in during the presentation. Again, Nydia, if you undock that question pane, it'll help you resize them. But the first one is, what graphite are you considering? What MFG, what type? All graphites are not the same, as you well know. So I believe you addressed that during your presentation, but do you want to talk again about that?
Correct. I'm trying to see, can you repeat the question again just to make sure that I...
What graphite are you considering? What MFG? What type?
So I'm not considering any graphite. I'm not building any reactor. So I think that's a question that every reactor designer will have to get hopefully some of the data that we generate in this campaign for a wide range of graphite grades that are available. So soil intrusion is not the only factor that needs to be taken into consideration. So that irradiation behavior, what lifetime, what operating conditions, and so on, all that has to be brought into the equation to be able to decide I'm going to choose that. But that's not a decision I do. I'm doing this again, trying to understand more generic and covering a wide range of graphite grades that are available, as you mentioned. And as I've shown here, there is a different geometries, porosity, and grades that are there. So, and I'm having an echo, Berta. I don't know if it's, I didn't have it before.
I'm sorry, I didn't understand the last thing that you said.
I'm having an echo here that I didn't have before.
Yes, it's because Berta thinks you need to mute yourself when she talks.
Okay. Can you please define edge site and basal site?
Okay, I wanted to say that MFG, and now I understand what manufacturing, I believe is what the person is referring to. And again, I cannot mention what are considering or recommending. I cannot recommend a graphite grade. That's just something the designer has to do. So next question on basal versus edge sites. Again, just going to that crystal structure, you know, your basal is just your surface. When you have that 2D hexagonal, then you got your plane, that's your basal planes. Your edge side would be the terminating sides for that plane. And again, those are the reactive sides. Those are the sites where you will have oxidation start. Those are the sites that could be reacting with other compounds to chemisorb or you know, have some reaction in there.
Thank you. Why submerge samples for 12 hours? What drove that time frame? And did you consider a longer exposure?
Yes, so our original 12 hours had to do a little bit with our safety in here. That was kind of before we were comfortable leaving the system overnight unattended for longer than 12 hours. That's what we were able to do, like coming early in the morning, having one shift submerging the sample and having somebody staying late and then removing in there. That also kind of is very similar to other values that you see in the literature. You see literature values of 12, 20 hours. Once we had done this several times and we talked with our ESNH people, our safety people, and demonstrated that, you know, our setup was safe to leave unattended, that's when we went to longer periods of time. And again, that second set of neutron imaging that I shows that samples for 12 hours and then 2 weeks. So we were able to leave our system immersed on the molten salt for up to 2 weeks.
Thank you. What are the consequences of salt intrusion on the reactor operation and safety?
Again, that I don't know. I cannot answer that because it is going to be all dependent on the type of reactor that you have. What are your operating conditions? What are you accounting for? So I think the designers, hopefully once we can provide information, or, you know, this amount of salt goes into the graphite grade that you're considering, and it goes into this many millimeters into the surface, so it migrates deeper. They can take that into consideration and make account that for the operation and account that for the safety case that they may do.
Thank you. In relation with the publication, Infiltration of Molten Fluoride Salts in Graphite, Phenomenology and Engineering, Considerations for Reactor Operations and Waste Disposal, and cites a Journal of Nuclear Materials. The presentation made, to what extent is the impact of the FLCNAC on disposal requirements have been studied theoretically or experimentally with or without disposal implementing organizations? That's a long one. I'm going to post.
Yeah, that's a good question, and I really do not have an answer for that. I'm not working on disposal requirements, so I don't I cannot answer that question right now. I'm sorry.
Thank you. Does irradiated salt intrusion make any difference than non-irradiated salt intrusion?
I don't know that yet. We are hoping to do some salt intrusion, so some irradiated graphite. If the person that is asking this, is familiar with irradiation effects on graphite, we know that as you irradiate, the neutron dose increases, these dimensional changes causes defects into their potentially, the porosity may be changing slightly. So it is likely that there may be some changes on that, but I have not done measurements. We do have in the plans for next fiscal year to get some irradiated graphite samples and do some comparison to non-irradiated.
Thank you. Do you have any plans to test other types of fluoride salts?
So right now we are approved to use FlyNac. Unfortunately, because of limited budget and all the extreme precautions of handling beryllium-containing salts, right now at this point we do not have any plans to move to Fly. So we're doing this more fundamental studies using FlyNac, but right now we don't have any plans to move to beryllium-containing or other or irradiated salts right now.
Thank you. Could you say a bit more on the time effect? Is there an indication that wetting increases with time, or is there something else that explains changes in the salt penetration with time?
That is an excellent question, and it's a question that we're asking ourselves and trying to study. Again, we're doing the contact angle. We're looking at different heating profiles, hold times. We see differences. We still cannot explain some of the things that we are observing, but certainly we're seeing differences. When we do the contact angle measurements, we're doing this at flowing argon, so there's not overpressure of argon, so there may be some changes again on the salt and how it behaves. So what we may be seeing when we do the contact angle may not be 100% representative of what the salt will be seeing when there is an overpressure in there. But certainly we are trying to understand that time effect. Whether there will be other factors like maybe it's surface finish or roughness of the surface, and again, certainly the pore structure that other surface may have an effect on that. So yes, good questions.
Thank you. How are you considering measuring mechanical or thermal properties of graphite that's been infiltrated with molten salt? Do you have any guidelines to do such measurements?
That's another excellent question, Mona. I didn't show here, but we did try to do this. And actually, we tried to do this before we did the imaging, and I'd always kind of say, okay, do we do it with the salt or without the salt? And this is very challenging because you do the exposures, you raise the temperature to have the molten salt, but you gotta extract the samples from there. You have to cool down, salt solidifies. Then if you do your measurements using standard SEM test methods, you got your salt is solid at those temperatures, or trying to adapt those testing measurements to high temperatures is not straightforward because, it's not, you not only need to increase the temperature, but you need to make sure you get an inert environment. So the question of whether we do the testing with or without the salt is been there. ASTM, at the ASTM committee, which I participate, we're having that discussion right now. The challenge, though, is removing the salt once it's gone into the pores of the graphite is not easy. So it doesn't want to come out. So, and what kind of additional damage are you causing to the graphite when you go through that cycle? And as you've seen, the profile of that salt distribution into the samples is not the same for all. So if you were to test with the salt in there, you may have samples where you have just salt accumulated on the edges versus salt across the cross section. That question again is being considered under ASTM, but there's no an answer yet for that because it's very challenging.
Thank you. Have you considered how salt intrusion into the graphite and graphite particulars in the salt due to wear affect the characteristics of the radioactive waste that need to be stored and disposed?
No, and that's not, currently it's not part of the scope of work that I'm addressing, but I do know the community is interested in that, and hopefully we will have budget available for the appropriate people to be looking into this. So, yeah, no, we have thought about it, we have talked about it, but not doing any research in that area right now.
Thank you. Do you expect to conduct similar experiments on impregnated or coated graphite? If yes, what type of impregnations, coatings do you anticipate to explore? Will you explore fuel salts?
Yes, so right now I'm not doing any modification to the graphite. I'm utilizing graphite as provided by the manufacturers. And so I'm not considering any coatings or impregnations of the graphite right now. And again, the question of the fuel salts right now is more an issue of our budget and scope of work still does not it's not there for us to explore the fuel salts. So we're doing again right now using fly mag most of the work that we're doing.
Thank you. Based on the testing performed, do you have an impression of the, quote, optimized graphite? What are you looking for as favorable parameters resulting from your testing?
Yeah, so again, this goes back to what I mentioned before. I cannot recommend a graphite, and I believe that what you call an optimized graphite is going to look very different from reactor design to reactor design based on what operating conditions, you know, what kind of pressures, what kind of temperatures, what kind of flow rates you have, what kind of, what are you accounting for or not. So I don't think there's such a thing as an optimized graphite for a generic molten salt reactor. It's just, again, it's just going to be the reactor designer who will take the information that we're providing, look at what the operating conditions is, deciding what they can live with or what they cannot live with, and how they can make a safety case, the NRC, and then from there decide the graphite. I also know there's a lot of other factors beside this, cost of the graphite, shape, size of the graphite, available have to be taken into consideration. So, yeah, there's not, in my opinion, I don't think there's such a thing as an optimized graphite, because there's not just a single reactor design or just a unique operating condition.
Thank you. I want to take this minute to thank you again, Dr. Gallego, for spending your time with us and sharing your expertise. It's greatly appreciated. That's the questions that have come in thus far. You can tell the interest in the topic just given the number of questions. It's always wonderful to see such engagement. I appreciate your time and willingness to field all of these questions.
Yeah, and anybody, Berta, if you know, I know a few of these names in here, so if they would like to reach out, want more information, feel free to contact me. I think my contact information was at the beginning of the slide. On
the Meet the Presenter slide is your email, so I thank you for that. Thank you for your willingness to go offline and talk with folks more directly. Trisha, do you have any concluding thoughts?
Yeah, just thank you so much again, Lydia. We work closely together. Thank you for the excellent presentation. I wish us to have a little bit more funding for next fiscal year. That will help. But thank you, extremely well presented. Thank you again, Nidia. And again, thank you, Bertha.
You're welcome. Thank you. Okay, with that, I'll close it out and we'll let people get back to their day. Thanks so much. Bye-bye.
Bye. Thank you.